Hello everyone, I'm Naoki Ebata, a master course student from Tohoku University in Japan. Today, I will introduce our research project, Polymorphic data layout for SX-Aurora TSUBASA vector engines. This is the outline of today's talk. First of all, I would like to explain the background and overview of our research. This is the background of our research. Recently, it is known that the performance of many applications, especially scientific applications, is limited by memory bandwidth. This is because the memory performance improvement has been much slower than the processor performance improvement. This problem is often called memory warp problem, and it is one of the key issues in the HPC community. As a result, today, in order to achieve high sustained performance, one of the most important requirements is to achieve high sustained memory bandwidth. To meet the demand for high memory bandwidth, some latest processors are equipped with high bandwidth memory. There are processors with more than 1 TB per second bandwidth, such as NVIDIA A100 and Fujitsu A64FX, and our target system, NEC SX-Aurora TSUBASA vector engine. Such a processor has a totally different memory architecture from standard CPU architecture, such as x86. Here, let me introduce our target system, SX-Aurora TSUBASA vector engine. Vector engine is a new vector processor developed by NEC Corporation. Vector engine has some unique features. First, very wide vector instruction set. Vector engine can perform 256 operations with one instruction. Second, very high memory bandwidth. Main memory of vector engine consists of 6 HBM2 memory modules and achieve 1.2 TB/s theoretical memory bandwidth in the case of Type 10B model. Thus, vector engine has both of powerful computational resources and wealthy memory capability. We can say that the vector engine is one of the most well-balanced processors. Third, vector engine is easy to use. Basically, vector engine supports standard C and C++ and Fortran code, so you don't need any special programming frameworks such as CUDA or OpenCL to use vector engine. Let's get back on track. In previous slides, we told the sustained memory bandwidth is a key factor of many scientific applications performance. Then, what is a key factor of sustained memory bandwidth? Yes, it's data layout. In order to fully exploit systems' potential memory bandwidth, data layout optimization is necessary. SOA versus AOS problem is a well-known example. CPUs and vector processors can efficiently process data mapped onto memory in structure of array layout. On the other hand, GPUs can sometimes process array of structure more efficiently than the structure of arrays. Thus, a suited data layout should be selected for each processor. And another example is padding. Padding is mainly done to avoid memory access conflicts. Later, we will explain padding in detail. Here, two problems have become clear. One is that a different data layout is required for each processors, because each of the processors has a different memory architecture. And SOA versus AOS in previous slide is a good example. The other problem is data layout optimization requires code modification and parameter tuning. They are not only tedious for programmers, but also error-prone. To solve these problems, polymorphic data layout has been proposed by some researchers. This figure shows the concept of polymorphic data layout. Our programming model abstracts data layout of arrays and internally map data on memory in suited layout for a target processor. Programmer write codes with API-provided programming models, and the backend of programming models selects efficient data layout and map on memory. This method enables to keep performance portability in terms of sustained memory bandwidth. Kokkos is one of the most popular programming models that support polymorphic data layout. Kokkos has been developed by Sandia National Laboratory, and many scientific applications are ported to Kokkos. Let me introduce Kokkos features. First, Kokkos is templated C++ class library. So you are familiar with C++, you will be able to use Kokkos easily. And second, Kokkos is portable across CPUs and GPU. And the third feature is polymorphic data layout. In Kokkos, polymorphic data layout is implemented in the form of array-like C++ class called view. Here, let's consider combining Kokkos and vector engine. Although Kokkos does not support vector engines officially, we confirm that C++ compiler of vector engine can build source code of Kokkos, and some benchmarks works. Note that we use Kokkos OpenMP host backend for vector engines. However, there is a problem that the data layout for standard CPUs is not necessarily suited for vector engine. As told in previous slides, required data layout optimization is totally different between processors. From here, it's part of our proposal. First of all, our goal is achieving performance portability in terms of sustained memory boundaries between vector engines and other processors. To achieve this objective, we propose polymorphic data layout for vector engine. Specifically, we incorporate vector engine specific data layout optimization mechanism into the backend of Kokkos. And as a first step of polymorphic data layout for vector engines, we target to eliminate negative effects on sustained memory boundaries caused by memory access conflicts. Today, most of main memories consist of multiple components such as memory module, channel, and bank. For example, the main memory of vector engine consists of 6 HBM2 memory modules, and each HBM2 memory modules is connected to the LLC by 8 channels. This means that there are 48 channels per vector engine. Also, the vector engine type 10B supports 32 memory banks per channel. So there are 1,536 memory banks in vector engine as a whole. These memory banks can be accessed independently, and it is effective to improve sustained memory boundaries. Sometimes multiple memory accesses to a specific memory component are issued simultaneously, and then they conflict each other. The conflict results in a long latency to process them, so memory access conflicts have a negative effect on sustained memory boundaries. Especially in vector engines, memory access conflicts at memory bank have a significant effect. See this figure. It's a performance of Kokkos stream, that is stream benchmark implemented with Kokkos. We measure the performance while changing its array size. X-axis is the array size and Y-axis is the measured sustained memory boundaries. Then we can see some point where the performance sharply drops. Here and here. Well, it is a negative effect of memory access conflicts. Frequent occurrence of memory access conflicts causes severe performance loss. Thus, memory access conflicts should be avoided. To avoid memory access conflicts, there is a well-known technique called padding. The occurrence of memory access conflicts depends on data layout, so changing data layout will be a solution of memory access conflicts problem. In padding, by allocating extra bytes for arrays, we change the data layout. If a suitable size of extra bytes is given, we can avoid conflicts. However, there are some problems in this technique. First, padding needs code modifications. It is against the policy of portability. Second, padding needs to tune padding size. Such a parameter tuning requires programmers to do tedious work in a trial and error manner. Third, it is difficult to notice the negative effect of memory access conflicts. Unless programmers have a knowledge of memory architecture, they may not notice it. Then, a good solution for those problems is polymorphic data layout. We propose a framework that can be the backend of polymorphic data layout and internally and automatically do efficient padding. Then, programmers even don't need to note the occurrence of memory access conflicts. Polymorphic data layouts do it all. Let me talk about how we can avoid memory access conflicts. First of all, note that our approach is based on our previous work. In the work, we have proposed an automated method to avoid memory access conflicts at vector engines memory bank. And in this work, we put that method into Kokkos backend. Let me talk about the scope of the method. The scope is to avoid inter-array conflicts, and that is memory access conflicts between accesses to elements to different arrays. this figure shows this. Yeah, this figure shows inter-array conflicts. Although there are other types of memory access conflicts, such as intra-array conflicts and inter-thread conflicts, uh, they are out of the scope because a great performance gain can be obtained only by avoiding inter-array conflicts. We will show it later. Our basic idea is simple. If the bank address of two arrays AI and BI are close in bank addresses, there is a high risk of frequent occurrence of memory access conflicts, like this figure. Thus, bank addresses of arrays, in this work, bank addresses of Kokkos view instances should be far from each other, like this figure. I will briefly explain our implementation. Our method is implemented in the constructor of Kokkos view. Originally, the constructor has a role to allocate memory region for the instance. In our implementation, we add one step here. We incorporate the mechanism to automatically apply padding, considering the difference in initial address from the other Kokkos view instances. This step is automated and completely hidden from programmers. I will briefly explain our method. First, each of Kokkos view instances is assigned a bank address in order shown in this figure. The first instance is here, and second one is here, and third one is here, and the fourth one is here, and the fifth one is here, and so on. Second, we derive the difference between assigned bank address and the bank address returned from malloc function. And third, pass the memory region with considering the difference in initial addresses or from other Kokkos view instances. Next is the evaluation part. We will demonstrate that our proposal successfully mitigates negative effect of memory access conflicts. This slide shows the experimental setup. System specification is as follows. We use type 10b model vector engine and the version of vector engine compiler is 3.0.6. And we use Kokkos 2.9.0 as a baseline of our implementation. And we use two benchmarks for evaluation, Stream and Himeno benchmark. Of course, both of them are implemented with Kokkos. We evaluated Stream benchmark using single core and Himeno benchmark using 8 core, and that is all cores of vector engine. Stream is a well-known benchmark that is used to measure sustained memory bandwidth. Stream consists of 4 kernels: copy, scale, add, and triad. The objective of this evaluation is to exclusively observe the effect of inter-array conflicts. There are no intra-array conflicts because all kernels of Stream has a stream type access patterns. Also, there are no inter-thread access conflicts because we execute it on a single core. This slide shows the evaluation results of copy kernel and scale kernel. X-axis shows the array size, and y-axis is the sustained memory bandwidth. And yellow point shows the performance of original Kokkos, and the green point shows the performance of our implementation. And then, in both kernels, there is no negative effect of memory access conflicts. So these kernels don't need a proposal. It's good result for vector engine users. However, in add kernel and triad kernel, we can see negative effect of memory access conflicts clearly. At some array sizes, the sustained memory bandwidth of original Kokkos drops sharply. On the other hand, our proposal keeps steadily high sustained memory bandwidth. And these results indicate that our approach successfully eliminates memory access conflicts under the conditions that only inter-array access conflicts occur. By the way, the difference in performance behaviors from two kernels shown in previous slides, so that is copy kernel and scale kernel, will be caused by the difference in the number of load operations per one loop iteration. Both copy and scale have one load and one store operations per one loop iteration. Since the store operation is executed after completing the load operation and the arithmetic operations, so there is a time difference between them. Thus, there is a low risk of memory access conflicts between these operations. On the other hand, the kernels in this slide, so add kernel and the triad kernel have two load and one store instructions per one loop iteration. So these two load operations could be conflict. Himeno benchmark has a main loop of a Jacobi method solving Poisson's equation. It is known that Himeno benchmark is a memory-intensive benchmark. The difference from stream is here there are intra-array and inter-thread memory access conflicts. Since Himeno has a stencil type access patterns, multiple elements of a specific array are accessed in a single iteration. Thus, intra-array access conflicts could occur. Also, since we execute Himeno using 8 cores, inter-thread conflicts could occur. This slide shows the evaluation results of Himeno benchmark. X-axis shows the problem size. We set the problem size to 256 times 256 times n. X-axis is the value of n, and y-axis shows the sustained performance in megaflops. Yellow is the result of original Kokkos, and green is the result of our proposal. Here, in both of original and proposal, some performance degradations are observed. For example, this point, this point, this point, and so on. But the degree of degradation is totally different between them. Also, negative effects coming from intra-array or inter-thread access conflicts can't be perfectly eliminated. But our proposal successfully mitigates the performance loss caused by memory access conflict. Here we can see an interesting phenomenon that the performance drops has a period. More specifically, the performance degradations occur at the problem size that is multiple of 3. This phenomenon can be explained as follows. Since we set the problem size to 256 times 256 times n, if n is multiple of 3, then the problem size becomes a multiple of 1536. That means the total number of banks. Because vector engines memory interleave use round-robin method. In such a case, memory access occurs at a specific bank simultaneously. Our proposal can automatically prevent such a situation, so it can consistently achieve high sustained memory boundaries. Now, let me summarize the talk. Recently, the performance of main scientific applications are memory bound and data layout optimization have become more important. Here, polymorphic data layout is an effective approach for high sustained memory boundaries and performance portability. In this work, we introduced polymorphic data layout into vector engines. As the first step on polymorphic data layout for vector engines, we incorporated the automatic padding mechanism into Kokkos, and we demonstrate that our proposed method is effective to mitigate negative effects of memory access conflicts. In conclusion, this work demonstrates the importance of data layout optimization to achieve high sustained memory boundaries for modern processors with high bandwidth memory modules. Kokkos offers an appropriate abstraction layer to hide the mechanism to automate the data layout optimization. We would like to acknowledge this project. That's all. Thank you for listening.